Hey everyone, and welcome to the Irish Hematology Oncology podcast. We aim for this podcast to be like grabbing a drink with a trusted colleague to discuss the latest in cancer care, break down complex topics, and share practical experiences. I'm your host, Owen Tabb. Today, we're going to dive into the fascinating world of systemic anti-cancer treatments, the medications that play a pivotal role in fighting cancer. Now, if you're a healthcare professional who doesn't spend their days immersed in the oncology world, this world of chemotherapy and targeted treatments can seem a bit daunting. Don't worry, that's why we're here. We're going to break things down and make it easy to understand. I was originally going to go through this episode in one go, but I think I'll break it down into 2 episodes. This is an absolute beast of a thing. So today we'll look at an introduction to systemic anti-cancer treatments, or SACT, and at the pharmacology of the older school, non-targeted therapies. Next week, we'll jump into the more specific targeted therapies. Now, to explain in this episode, I always find these pharmacological pathways difficult to understand. So I'm going to break it down into simple analogies to try and make it easy. So firstly, first segment, what are systemic anti-cancer treatments? When we hear the word cancer, most of us picture a tumour, a localized growth of abnormal cells. However, cancer's reach can far exceed a single visible mass. Systemic anti-cancer therapies are designed to tackle the hidden, travelling aspects of cancer that traditional therapies like surgery or radiation may not fully address. So cancer can spread in a few different ways. So you have local invasion. Imagine the root system of a plant. Cancer cells can extend into the surrounding healthy tissues, making complete surgical removal a challenge. So think of those roots spreading out and going into the surrounding healthy tissue. Then we also have lymphatic spread. The lymphatic system is like a motorway network for fluids and immune cells. Cancer cells can hijack this system and they travel to nearby lymph nodes or even distant organs. Then you can also have bloodstream spread. Just as they can with the lymphatic system, cancer cells can infiltrate the bloodstream. This allows them to set up shop in far-off locations, creating new tumours known as metastases. So why do we need systemic treatments? Well, surgery excels at removing localized tumours, and radiation therapy can precisely target specific areas of cancer growth. But what about the cancer cells that have already escaped notice? This is where systemic anti-cancer treatments play a pivotal role. These treatments are administered in various ways, including orally, so taken by mouth like standard pills or capsules, and intravenously, so IV, injected or infused directly into a vein, and this allows the medication to quickly travel throughout the bloodstream. And then there's other routes, so some treatments might be injected under the skin, into a muscle, or other less common methods. So now let's look at how systemic treatments work. Think of search and destroy. Picture these treatments as highly specialized search teams traveling throughout the body. Depending on the medication type, they use different strategies to find and disable cancer cells. So one of those ways is disrupting cell growth. Many systemic medications focus on stopping cancer cells from dividing and multiplying. Think of it as cutting off their supply lines or sabotaging their reproduction process. Then you could also do a targeted attack. Newer therapies often home in on specific proteins or pathways that cancer cells depend on to survive. It's like blocking the unique radio frequency cancer cells use to communicate and thrive. And then you could also do an immune system boost. Some treatments work by revving up your own immune system, helping it recognize and eliminate cancer cells it might have otherwise ignored. So let's think about cancer cells as weeds in a garden. Surgery is like pulling up the most visible weeds, while radiation is akin to scorching a specific patch of weeds with a magnifying glass. Systemic treatments are similar to applying a weed killer that travels throughout the entire garden soil system, targeting those hidden weeds and preventing new ones from sprouting. Systemic anti-cancer treatments are a crucial part of the cancer fighting toolbox. They're rarely used in isolation. Often they are employed in conjunction with surgery. They might be given before surgery, neoadjuvant is the term for that, to shrink a tumour, or after surgery, adjuvant is the term for that, to eliminate any microscopic cancer cells that are left behind. Then you have radiation therapy. So they can be used in conjunction with that. Systemic treatments can make cancer cells more vulnerable to radiation or help deal with any distant spread that radiation therapy can't reach. So important to note, look, even while explaining the power of these drugs in accessible ways, it's vital to acknowledge that systemic anti-cancer treatments are powerful medicines with unique considerations and side effects. We'll address that later in this podcast. So let's move on to discussing the wide variety of systemic treatments available. We'll take a quick break here and we'll return and get to that next. Okay, welcome back. We're going to jump into the second segment now of the cytotoxic chemotherapy drugs, those guys that disrupt the essence of cancer cell growth. So cytotoxic chemotherapy drugs have been a cornerstone of cancer treatment for decades. Their name says it all. Cyto means cell and toxic means poisonous or toxic. These potent medications act by causing direct damage or interfering with processes essential for cancer cell replication. Though they target both cancer cells and rapidly dividing healthy cells, the overall risk-benefit is disrupting cancer's uncontrolled growth. So you get that overall benefit by disrupting that growth. Let's break down the main categories of cytotoxic drugs and how they work. So firstly, we'll look at alkylating agents. These are DNA saboteurs. Alkylating agents wage war on a cancer cell's most precious asset, its DNA. Their chemical structures allow them to attach alkyl groups, which are basically carbon-based chains, to the DNA strands. This is where the sabotage begins. So firstly, we've got this cross-linking chaos, right? Imagine that DNA strands are two intertwined ropes. Alkylating agents act like chemical handcuffs. They create abnormal links between the strands. This prevents the DNA from unzipping and being copied, which is essential for cell division and ultimately cell replication. What else do? They also break the blueprint. These agents also directly break strands of the DNA. This isn't a clean surgical cut, it's like tearing pages from the cellular instruction manual. With vital information missing or scrambles, cells can no longer replicate, causing them to self-destruct. So let's look at a few key examples, right? Alkylating agents are a diverse group with some of the heaviest hitters going. So we've got cyclophosphamide and ifosfamide. These are powerhouses that are used for solid tumors and for hematological cancers as well. Melphalan is another example. It can be used in multiple myeloma. And the carbazine, this is often used in melanoma, skin cancer, and also in some lymphomas as well, like Hodgkin's lymphoma. So now, I said at the start of the podcast that I'd like to break these things down and use analogies to give us an example as to an easy method for remembering how these guys work. So we'll look at the alkylating agents like a construction site sabotage, right? Think of a construction crew diligently following a master blueprint to build a skyscraper. Now imagine someone sneaking onto the site with these goals, right? To do tangled tools, right? They weld some of the tools together that render them useless and halting work. This is like the cross-linking action of alkylating agents on DNA. They could also go onto the site and they rip up the plans. They tear pages from the blueprint, leaving whole sections incomplete. This mirrors the way these drugs can break into the DNA's instructions. And also, imagine they scribble over sections. So to add even more confusion, they cover important measurements and diagrams with nonsensical scribbles. This extra layer of chaos is much like the way alkyl groups disrupt the DNA code. So hopefully that's helpful for you. Next, we have antimetabolites, right? These are imposters with a mission. Antimetabolites are masters of disguise within the realm of cancer treatment. They are molecular mimics, closely resembling the essential building blocks that cells need to create new DNA during replication. However, they have a sinister goal: to sabotage the process from within. So let's look at cellular counterfeits, right? Antimetabolites are like counterfeit bricks. They have just enough structural similarity to sneak into the DNA construction project, but once incorporated, everything falls apart. They are flawed parts that destabilize the entire structure. They're also replication roadblock, right? Imagine a cell trying to photocopy its DNA. Antimetabolites get mixed in with the regular ink for the copies. This leads to faulty, illegible sections of DNA, and the whole process grinds to a halt. So there's a few key examples here of notorious antimetabolite imposters. So 5-fluorouracil, or 5-FU. It's a master of mimicking a building block of DNA, causing widespread errors in replication. Methotrexate, it interferes with a critical vitamin, folate, that cells need to create components of DNA. Gemcitabine, another DNA mimic with a disruptive mission, used broadly across several cancer types. So for this analogy, we're going to use the cake imposter. So imagine a master baker crafting a multi-layered cake. Each layer requires a specific ingredient. Let's say a key one is almond for the flour, right? Now imagine someone secretly swaps the portion of the almond flour with sawdust. Visually, it looks almost the same. But as the baker builds the cake, structural problems emerge, right? You get these crumbly layers. Sawdust doesn't bind like flour. The layers become unstable and prone to collapse. This mirrors how faulty antimetabolite bricks make the DNA structure weak. And an inconsistent flavor also develops, right? Sawdust disrupts the taste of the cake, making the final product inedible. This parallels to the way antimetabolites render the newly copied DNA illegible and unusable. These imposters are powerful because they exploit processes that cancer cells desperately rely on to keep dividing. While a fast-growing cake might be okay, fast-growing cancer definitely isn't. So now we'll look at the third group, right? Mitotic inhibitors, stalling cell division in its tracks, right? These are antimicrotubule agents. So microtubules are the tiny tubular structures within cells. They form a dynamic network that serves many crucial functions. During cell division, they become the backbone of the mitotic spindle, responsible for the intricate dance of chromosome separation. Antimicrotubule agents exploit this reliance, targeting microtubules to put a halt to the runaway division of cancer cells. I recommend looking at a diagram of the cell division process, or mitosis, to kind of have a look, see what these little microtubules and mitotic spindles look like. So let's dissect the two main classes of these agents, right? Firstly, we've got vinca alkaloids. They prevent the spindle assembly, right? So vinca alkaloids are derived from the periwinkle plant. Vinca alkaloids like vinblastine and vincristine act by binding directly to tubulin, which is the essential building block of microtubules. This binding prevents microtubules from being assembled, essentially leaving the mitotic spindle without a framework to build upon. The cell becomes stuck in metaphase, unable to complete division. So we'll use a quick analogy here. Imagine constructing a tent, right? Vinca alkaloids are like preventing the poles from ever being connected in the first place. No framework, no tent. Secondly, let's look at taxanes. They're creating faulty spindles. So the mechanism of action for these guys they're derived from yew trees. Taxanes, so the drugs are paclitaxel and docetaxel, work a bit differently. They also bind to tubulin, but promote the formation of too many microtubules, and these microtubules are abnormally stable and dysfunctional. The result is a chaotic, unusable mitotic spindle that leads to cell death. So the analogy here, again, let's go back to the tent. Imagine the tent being built with splintered poles haphazardly jammed together. The whole structure is unstable and can't fulfill its function. These drugs have broad applications across many cancer types. Some specific examples include the vinca alkaloids. These are used extensively in lymphomas, some leukemias, lung cancer, and a couple of others. Taxanes are highly effective in breast cancer, ovarian cancer, lung cancer, and several other tumor types as well. The fourth category we're going to go into are the DNA topoisomerase inhibitors. They cause a targeted breakage and leave DNA permanently damaged. Topoisomerases are enzymes that manage to supercoil DNA within a cell's nucleus. Imagine them as tiny untanglers that temporarily break and rejoin DNA strands. Topoisomerase inhibitors block these enzymes, causing breaks in the DNA to remain open. These breaks trigger the cell to self-destruct. There are two main types, right? So there's type 1 topoisomerase inhibitors, and the example of that is irinotecan. They block the rejoining of single-strand DNA breaks created by the enzyme. And then you've got the type 2 topoisomerase inhibitors. And the examples of these are doxorubicin and etoposide. And these guys block rejoining of double-stranded DNA breaks caused by the enzyme. So type 1 single strand, type 2 double strand. In both cases, the unsealed breaks are too big a problem for the cell to fix, leading to programmed cell death. Another term for that is apoptosis. So we'll go into our analogy here. So think of the topoisomerases like the repair crew for a tangled phone cord. They temporarily cut the cord, they untangle it, and then they neatly reseal. So topoisomerase inhibitors prevent that resealing step, leaving the cord in a permanently frayed state that triggers a junket response or just kill the whole cell. These drugs also have a wide application in cancer treatments. They can be used in small cell lung cancers, ovarian cancers, colorectal cancers, certain leukemias, and lymphomas. So cytotoxic chemotherapy has played a major role in cancer treatment for decades, and it continues to be a valuable tool in our arsenal against this complex disease. It's important to note that these are just some of the many cytotoxic chemotherapy drugs available. Each drug has its own specific mechanism of action and side effect profile. I've kept it quite vague today just to try and get those couple of mechanisms kind of clear in everybody's head. Cytotoxic drugs are often used in combination regimens as well, so where multiple drugs with different mechanisms of action are used together. This approach can improve treatment efficacy and reduce the chance of cancer cells developing resistance to any single drug. Due to their non-specific nature, though, cytotoxic drugs can also damage healthy cells that are rapidly dividing, leading to side effects such as nausea, vomiting, fatigue, and hair loss. We'll touch on all side effects and stuff when we go into some of the specific treatments and the specific cancers later on in our podcast series. Well, that wraps up our overview of systemic anti-cancer treatments. While we focus today on the older cytotoxic chemotherapy classes, this is just the beginning. Understanding how these drugs work is the crucial first step towards understanding how to manage them and how to care for people receiving them. In our next episode, we'll dive into the world of targeted therapies and immunotherapy, the exciting new frontiers in cancer care. Thanks as always for joining me on the Irish Hematology Oncology podcast. If this was helpful for you, please subscribe and leave a review. Your support helps us to keep doing this and reaching more people with valuable information on all aspects of cancer care. Fill out the feedback form to give me an idea if this has been helpful, how we can improve, and any future episodes or topics you'd like to hear. And don't forget to log that important CPD. An example can be found in the show notes below. As always, I end with this important disclaimer. This podcast is for educational purposes only. Remember, the field of cancer care is always advancing and new research may lead to changes in treatment approaches or protocols. Always consult with your own team for personalized guidance and discuss any information from this podcast with them. Seek information from trusted local and national resources for the most up-to-date recommendations. Okay, catch you next week for part 2 of Pharmacology. See you guys.